going to look at a problem to do with induction today. So specifically a solenoid, which when a current goes through it becomes a big electromagnet. So the current that a solenoid induces into another loop of wire, then we're going to look at a few kind of variations on that. So our solenoid, we're told it's very long compared to its cross-sectional area. So we're just going to model it as a big sort of one-dimensional thing really when we're looking at the solenoid. So the current going through it at any time oscillates like this here. So this is our expression for current. So I at any point is the maximum value of I multiplied by cos omega t, where omega is the frequency and t is it's the sort of the radial frequency, the angular frequency, and t is again just time. And we know the solenoid has n turns in it. So a solenoid is just a big coil of wires. Don't you know the turns in it? The more turns, the stronger the magnet is. And then, so inside this solenoid, we're going to insert a loop of wire. And we know the loop, it has k turns. It has a radius given by r, and it's oriented at an angle I'm going to call theta. So it's important because if the loop, or if the magnetic field lines from the loop and from the solenoid are parallel to each other, you won't get any current induced. You got to have them being perpendicular is your maximum. So that'll come up in a wee minute. So we want to find the current induced into the loop. So how do we find current through any kind of circuit, any kind of system? We normally use what we might call Ohm's law here. So, I forgot to say, the loop wire has resistance R. So we want to find the current. We already have the resistance, so we need to find the voltage, or in this case we might call that the electromotive force, the EMF. So we need, so this is just to find a step-by-step approach of how to solve this problem. So we need the EMF, electromotive force, which is like a voltage. It's not really a force at all. And how do we find the EMF? Well, EMF is rate of change of electromagnetic flux. Negative due to Lenz's law. So whenever you change flux, you'll feel a resistance. So the electromotive force and the flux are working antagonistically to each other. So that's what that is. This is just an expression of Faraday's law. So we want flux. And what is flux? Well, flux is the amount of magnetic field lines going through a surface. So it's the surface integral of the B field going through a surface with area A, which is great. Okay, so we want to find maybe an expression for this B field now. So that's where we're going to start, because the B field, well, we can use something called Ampere's law. Sometimes get Ampere's law and Gauss's law mixed up, but it's kind of easy to remember. You think ampere, amps, and this one has expression for current in it. Okay, so We want to find the magnetic field inside the solenoid, because that's what we're looking at. We're looking at this loop is being inserted into the solenoid, so anything going outside is kind of irrelevant. Well, yeah, it is irrelevant to this problem. So we have n turns. I should have said this was per unit length, and yeah, because we have that, we're maybe going to look at the magnetic field not as a whole, but sort of more as a per unit length thing. So the magnetic field inside the solenoid per unit length is equal to, so we sort of divide by L here, so we don't have to do this integral. So this is our expression. Great, so we have the magnetic field, so now we can go and look and try and get the flux. So we're working backwards down this pattern, so we get magnetic field, then flux, then EMF, and then we get our current, and that's us at the end. So to get the flux, we then use this expression, so surface, so I want the flux that's going through the loop of wire, so I want to find the area of the wire that it's going through. So the area of the wire is equal to, pi over r, pi r squared, just a loop of wire. So we know our expression for the area of a circle is pi r squared, but it also is k loops, so we need to multiply that for every loop of wire that's going through. B k pi r squared. But also remember we said that it may be oriented at a slightly different angle. So theta 0 is perpendicular, we say that's kind of our zero origin where we're coming from. And we can multiply this by cos theta. So if it's 90 degrees away, or from being perpendicular, i.e. parallel, then this flux will be zero, because nothing will be going through, it'll just be going parallel to it. You know, it's not going like this, it's going like this, and nothing's going through if this hand is the loop of wire. So there we have it, and we have we'll maybe not just sub anything in, just no, we will. So then our next step is to find our EMF. So we want to differentiate the flux with respect to time, but we don't have a time component with respect to time in here, it seems, just yet, except we have B. So then we can then write this as B, or no, sorry, N, permeability of free space multiplied by current, times by K pi R squared cos theta. Still no term with respect to T, but remember we said earlier that the current is equal to I naught cos omega T, which gives us I naught, I'll do it this way, N pi K mu, permeability constant, multiplied by I naught cos omega T. I am sorry for this squeaking. Cos theta. Oh, that's better. Yeah, cos theta. Okay. So we have an expression with respect to time, so we need to find our EMF. So I'll just rub this out for now. So then EMF Emf is equal to rate of change of magnetic flux. So we just differentiate this. All of this can be treated as a constant apart from this cost term. So we take this W at the front. By our chain rule, cost will become negative sine. So I'm just going to write sine here, so that'll cancel with this negative from Lenz's law. Sine T n u naught k I r squared I naught cos theta. So then we're nearly there. V equals IR. Our goal at in the first place was to find current, so we just divide this whole expression by R. R being the resistance that we were given at the start. Wonderful. And that's it. That's the current that's induced by the solenoid into the loop of wire. So maybe we can change this up a little bit. Maybe we could say, what if instead of a coil of wire we put in another solenoid? So let me find my notes here. So we'll do the same thing as before. So our steps last time were to find the B field, so that then we could find an expression for flux, then EMF, and then current. So we'll do the same thing again. We'll find an expression for the beta field. No, the B. No, well, we already know actually. We've got the same solenoid actually, so we don't need to find another expression for B. We can just use our one from before that said B equals N U naught I. Okay, so we have our solenoids. Then our flux through our solenoid, well, it's just going to be the same kind of deal. So here we go. The area. So our solenoid, it'll have K turns just like our wire had K loops. So then, that looks very similar. Okay. That's the same. It's orientated at an angle cos theta. It's maybe not put in parallel, but there you go. So then from this expression we want to find the EMF through the solenoid, which is found the same way. That shouldn't be like a delta. Which will give us, if we substitute this in with I equals I naught cos omega t, well then, funny enough, we just get the same expression as before. I naught k I r squared sine omega t cos theta. And then to find the current going through this second solenoid that's inserted into our first solenoid, we just divide by R again. So we have divided by whatever the resistance of this new solenoid is. So there's no change. It doesn't matter if it's stretched as a loop or as a solenoid. the same sort of induction will go on. So that was a bit boring. So yeah, let's do something that's a little more involved, a little more exciting. So we're going to look at that same original solenoid. So all of the parameters to do with it are the same, except that now we're going to insert a soft iron core through it. So we have our solenoid, and then we're going to insert a soft iron core through it, okay, with permeability R. Okay, except that at one point along this, sorry for the squeak, there's going to be a little gap. It can be called G. Okay, so we want to know things about the current inside this solenoid through this thing that's now, we should call it an electromagnet now because it's a solenoid with a soft iron core. So we want to look at the field that's going through the inside of it, this internal field. So for this we have to start looking at what's called the auxiliary field. Expression for it is, that's magnetization and that's your magnetic field. But yeah, we'll not worry about that so much. We just know that because we're looking internally now into a solid structure, we gotta then write our Ampere's law. Now with respect to this auxiliary field, okay? So I want to find the auxiliary field along this, so we can divide this into three sections. So we have the first bit with a soft iron core, then our gap, and then our second bit with a soft iron core. So we can say that this equals the auxiliary field with iron in it multiplied by the length of that plus 2 plus H gap multiplied by, let's call that delta, well there's a wee missing gap in here. So, I've lost my place now. Yes, we have the current enclosed, and we can say that, I suppose it's important to say that this new never mind. So the current enclosed here are, yeah, so this part of the equation, because H equals B field divided by that, take away the magnetization. We don't really have to worry about this term. We're not really talking about magnetization here. That's not really a factor here. We can divide by this here, so that term really shouldn't be there. And so this all becomes the current that's going through this solenoid, same current that's been going through the whole time. I equals I naught cos omega t, whatever it is, so equals I. But then we also need to consider how many how many turns are going through here as well. So we have n turns per unit length, and we'll call f the length here. So where f is equal to L1 plus L2 plus the length of the gap. So there we go. Starting to get somewhere. One other expression for the auxiliary field is this here relation between the magnetic field and the auxiliary field. Anyway, maybe that was a better example to use for why we got rid of that there, rather than the one with magnetization. You can just divide through by here. So here we are, our permeability of free space and of iron. Okay, so for iron, we can say of the auxiliary field that equals this here, and for the gap, because this term won't come into it because there's no iron there, we will have so it's the magnetic field going through the gap divided by the permeability of free space. The H field for these bits with iron, you gotta divide by both because they're both a factor in that. So yeah, now this gets a little bit, I can't really explain this very well, but we gotta look at the boundary conditions between these guys here. So because these guys are all sitting, the magnetic fields are all sitting perpendicular to each other, we know that the beta fields at the boundaries are going to be equal to each other. So we can say that the rather than just calling this one, we can call this the B field, the magnetic field in the iron. The boundary condition perpendicular to it is the same as the magnetic field through the gap perpendicular to it. And from this, and what we looked at with magnetic flux earlier, we can say that because these have the same areas, and just write this out again just so it's clear. The flux is equal to the magnetic field lines going through an area, and these have the same area because they're going through the same uniform solenoid. We can then say that the magnetic flux in the iron is equal to the magnetic flux through the gap. And because of this expression, we can say that we'll just call this a generic term for flux now. So this is flux multiplied by area, cross-sectional area through here. Okay, and then plugging that into here. I should say that. Yeah. So plugging that back up into these guys, we have H field through iron is equal to, a bit all over the place, I'm sorry, is equal to flux, just a generic term for flux now because we know they're both the same. H for the gap is equal to flux divided by area, and there's no mu naught term because there's no iron. I think what I have to keep here, yeah, let's keep those up for now. Okay, so let's go back to this expression. So now we can sub in our H fields here, and yeah, start getting closer to finding the magnetic field in this gap. Did I say earlier that's what we were trying to do? You know, I don't think I did. What we're trying to do is find the magnetic field in this gap where there is no iron core. Okay? It's dreadful. Anyway, here we go. It's equal to, so the is equal to this guy. Well, yeah. I'm going to factorize this and say that the flux multiplied by, on the right, the number 2, equal to A, not AR. And I'll multiply that by L plus L2 just to save a bit of space here, and plus through the gap A, and then we'll substitute our expressions for the flux back in. Remember, the flux was equal to the B field through the gap multiplied by area. So here we go. B over mu naught mu r, these a's cancel out, L1 plus L2 plus B mu naught times by delta. And these are the beta fields in the gap, which is what we're trying to find, which is great. So now it's just a wee bit of swapping things around. Maybe I need to write bigger. We also know this is equal to I n multiplied by f, which is this, L1 plus L2 plus delta. With a bit of swapping around, you should come up with the expression the field through the gap is equal to mu naught I n d. That's the way I like to write it, but I don't know, it might be more useful to write it as, to write these L1 plus L2 as the full length minus the length of the gap. Maybe that would be useful. Oh. And then you could divide through and have ratios of the length of the solenoid to the length of the gap and get information that way. But doesn't matter that much, I don't think. So, as your gap gets smaller and smaller, that'll equal 0, that'll equal 0, that'll just equal f, 2 f's will cancel, and you'll just get mu naught mu r I times n, which is the same as the magnetic field that we had to begin with before in the iron core, just multiplied by this factor here. Yeah, it's a bit disjointed, but I feel like I know it better, even if I've confused anyone who's watching this. But yeah, if anyone can give an explanation of why we use the auxiliary field here instead of just the plain old magnetic field, I would appreciate that, because I'm not sure. There's some sort of fuzzy ideas in my head about, oh yeah, because we're talking about things going through a solid now, but yeah, it's not really satisfactory. But if anyone has that, I would appreciate that.